In this video, I'm going to discuss an ideal gas undergoing an adiabatic process. And I'm going to do a derivation that actually gives me a relationship between the pressure and the volume. So at the end of this video, I'm going to give you a relationship between the pressure and volume that describes an ideal gas undergoing an adiabatic process. So to do this derivation, I'm going to need some relationships. I'm going to have to invoke some theorems. First of all, I'm going to have to invoke the Equipartition Theorem. That links the internal energy with the temperature. All of these guys here are just constants for the purposes of this system. So F is the number of degrees of freedom, capital N is the number of particles, K is Boltzmann's constant, and T over here, that's the temperature. So all these guys are staying constant. This can change and this can change. So what this equipartition theorem is saying for our purposes is that a tiny nudge in temperature has a direct correlation with a tiny nudge in the internal energy. So changing the temperature changes the internal energy. That's what this equipartition theorem is saying. And we're going to have to use this as our first step to do this derivation. The next thing we're going to need is the first law of thermodynamics. Now that states that the change in internal energy is due to either heat or work. So heat is represented by capital Q and work is represented by capital W. And this delta U is the change in internal energy. So what we can now do is actually apply the condition for an adiabatic process, which is Q equals 0. This is a thermally insulated system. There's no heat flowing in and there's no heat flowing out. So Q is equal to 0. And that implies, with the first law of thermodynamics, that delta U is equal to W, right? This Q just disappears, and we have this equivalence here. So the change in internal energy is just due to the work. And what is the work during a quasi-static compression or expansion? Well, it is minus P delta V, where delta V is the change in volume and P is the pressure. This minus sign is here by convention, because if we have a positive change in volume, if it's expanding, then the gas loses energy, right? It's doing work against the surroundings, so it's losing its energy. So if this is positive, then the work is negative. Then, if we also consider the other case, if this guy is negative, if you have compression, if the volume is getting smaller, this will be negative, and then a negative times a negative will give a positive quantity. So doing work on the gas by compressing it increases its internal energy. And the only way we can actually change the internal energy of an ideal gas in an adiabatic process is through work. There is no heat. That's this condition Q equals 0. So these guys are what we're going to end up using. So before we start this derivation, I just want to have a quick note of the ideal gas law, because we're going to need to invoke the ideal gas law in this derivation. So you might have seen PV equals nRT with a lowercase n. That's talking about the number of moles, and capital R would be the gas constant. These guys are actually equivalent to that, but what we're talking about is the number of particles, because in this derivation, we're interested in the number of particles, not the number of moles. So keep in mind, this is just another way of representing the ideal gas law. PV equals nKT. And this is a capital N, which is the number of particles. It's not the number of moles of particles. So a lowercase n would be the number of moles. So let's get started. The first thing that we can see from these relationships are this equipartition theorem describes the internal energy, and this over here is related to the internal energy. So that means we can equate two different expressions for a change in the internal energy. So I'm going to start off by writing du. So du is a tiny change in the internal energy. How can we write this? Well, using the equipartition theorem, we can actually write this as F on 2 and K dt. Now, can you see how I got this? This over here, F on 2 and K, that's just these constants out the front. We've got an NK, and we have, I've just brought this guy as a quotient, a little fraction, F on 2. So half the number of degrees of freedom times the number of particles times Boltzmann's constant. That is just a constant. This over here is a tiny change in the temperature, and that's going to cause a tiny change in the internal energy. What is another way we can write this tiny change in internal energy? Well, we can use this little trick that we have over here, and we can write it as a tiny little nudge in the work, right? Because the work is equivalent to the change in internal energy. So that means we can write this as a little differential. So we can have this equal to minus P dV, right? That's what this is here. Over here I'm writing it with a delta, and over here I'm writing it with a delta. This is saying it's like a change, but over here I'm going to write it as a differential, a little dV, a little dt, and a du, because we're going to end up integrating things. We're going to have to take the cumulative effect. So just keep in mind, this is the work done in a compression expansion process, and it has to be quasi-static. So quasi-static means that every single quantity has to be defined throughout the entire duration of the process. You can't have any point where there is an abrupt change where either the pressure or the volume or the temperature is undefined. That would not be a quasi-static process, and we wouldn't actually be able to describe that with this kind of theory. So what have we done? We have two separate expressions for the change in the internal energy. So a tiny change in the internal energy is either given by a tiny change in the temperature with some constants out the front, or it's the negative of pressure times a tiny change in the volume. So that's P dV. So this is the work, and this is from the Equipartition Theorem. Now what we can do is we can take this ideal gas law and we can rewrite this P. So have a look at this. This ideal gas law can be rewritten as P equals, we can just divide both sides by V. We can have N K T over V, right? I'm just dividing by volume, NKT over V. So I can substitute this into this. So let's go ahead and do that. So we're going to have F on 2 times NK dt. That's from the Equipartition Theorem. And then from the ideal gas law, I'm going to have NKT over V times dV. That's what I'm going to have over here. So what is this saying? This is just the ideal gas law substituted in here. Now what I can immediately do is I can cancel out NK and NK because it appears on both sides. And what I can also do is multiply both sides by 1 over t, or divide both sides by t. So I can move this t to the other side. And what's that going to give me? That's going to give me F on 2. So the NKs have disappeared. I'm going to have dt over t. That's this ratio. And that's going to be equal to negative, this NK has disappeared, this t we've divided through, so that's disappeared, dV over V. So this over here, this is the relationship we have now. Now you can see why I've been using these little differentials is because we're going to have to integrate this. So how do we integrate this? Well, I'll write the integral expression below. We're going to integrate from the initial temperature to the final temperature. So that's T sub I to T final. So this is T final. That F is not the degrees of freedom, it's the final temperature. And we're going to have dt over capital T, which is temperature. And then that's going to be equal to minus the integral from the initial volume to the final volume of dV over V. Now, what we're going to have to do is we're going to have to evaluate these two integrals. How would we evaluate these two integrals? Well, what is 1 over x integrated? 1 over x integrated, that's ln x, right? ln x is the natural logarithm. So we're going to have a natural log over here. We're going to have a natural log over here. And when we evaluate the natural log at the beginning and end points, we're going to have natural log of something minus natural log of something. And what does that mean? We can use log laws, and we can turn that into a ratio. So natural log of the final state over the initial state. So let's write that as well. So we're going to have f on 2, and then we're going to have natural log of t final over t initial, and that's going to be equal to negative ln, so this is natural log of v final over v initial. Right? So this, anytime you see this sort of integral, this pops up a lot in thermodynamics. You're going to have to just say, okay, that's the natural log of this ratio of the final over the initial. Now what we can do is we can use some more log laws. We can take this minus sign, take it inside, and anytime you raise something to -1, it's the same as taking the reciprocal. So we're going to have to flip these guys around. And we can also take this f on 2, and we can move that inside, and it's going to turn into an exponent as well. So what are we going to get? We're going to get natural log of t final over t initial to the power of f on 2. Right? So we raise this to the power of f on 2, and then we take the natural log. And that's equivalent to moving this constant out the front. And that's the same as natural log of v final over v initial. Oh, actually, we have to take the negative of that, so we reciprocate, and then we get v initial over v final. So that's what this is over here. Now, what we can do is we can say e to the power of this side and e to the power of this side, and we can get rid of these natural logs. We can exponentiate both sides, and that's going to get rid of all of this natural log business. So if we do that, we're going to get t final over t initial to the power of f on 2 is equal to v initial over v final. And now what we can do is we can distribute this exponentiation to both of these guys in the fraction. And that's going to give us the condition tf to the power of f on 2 times v final, right? I'm bringing this v final into that side. That's going to be equal to t initial to the power of f on 2. And then we have v initial, because v initial is already on the right-hand side. Now, I want you to be comfortable with this. We have just moved this guy to that side, and we've moved this guy to that side after applying the exponent. So that gives us this condition. Now, this is actually, we could actually stop here, and this is a very useful relationship between the temperature and the volume for an adiabatic process with an ideal gas. But what I'm looking for is pressure and volume. So we're going to do some more modifications to this, and that's going to give us a relationship between the pressure and the volume. So again, what we can do is invoke the ideal gas law. And the ideal gas law can be used on this temperature because we want to get rid of the temperature. But before we do that, we have to get this exponent off of the temperature and move it onto the volume. So let's do that. That's going to give us Tf, so the final temperature. And if we exponentiate the reciprocal, we take both sides and we exponentiate them to the power of 2 over f, then that's going to cancel on the top of these guys, and that's going to give us 2 over f over here, and we're going to get the same thing on the other side, 2 over f. Right, so all I've done is I've flipped these guys around by taking the exponent, taking both sides to the power of 2 over f. So that's what this is. This condition is also valid. Now what we can do is we can rewrite temperature in terms of the ideal gas law. And I'll do that up here, but before I do that, I'm just going to do a quick little note. You can write temperature equal to PV over NK. So this is NK. You could also use lowercase n and R, capital R, and that would be in terms of moles. So this temperature can be written as PV on NK. Right? That's exactly the same as a rearrangement of the ideal gas law stated up here. Right? We've just divided both sides by NK. So that's temperature. And we're going to substitute this into each of these guys. And I'll do that up here. So what I'm going to have is P final, V final over NK. And I'll put that in brackets. So that's from this temperature. And I'll have that version over here as well on the other side. But let me write this V final as well. So we got V final to the power of 2 on F. And that's equal to, see if I can fit it in here, got the initial pressure, the initial volume over NK, and then we have the initial volume to the power of 2 over F. So what have I done? I've just substituted this in place of the two temperatures. And you can see that each of these guys have the corresponding subscripts. This has the finals, this has the initials. Now what we can do is we see that there's nk on both sides, so we can cancel that again. That's not even going to matter. And what we can do is we can group these v's together, right? This is implicitly vf to the power of 1, and this is vi to the power of 1. And our exponent laws tells us that you can actually combine these guys when they're multiplied. All you have to do is add the exponents. So this is going to be 1 plus 2 over f. So let's go ahead and do that. That's going to give us p final times v final to the 1 plus 2 over f. And that's equal to p initial times v initial to the 1 plus 2 over f. So that's what this is over here. And what is 1 plus 2 over f? So I'll write that underneath. 1 plus 2 over f, that's exactly the same as f over f plus 2 over f. And that is f plus 2 over f. And what is this? This is actually gamma. So the degrees of freedom, the number of degrees of freedom plus 2 divided by the number of degrees of freedom, that is gamma. So what we can do is we can replace this over here by gamma, and that gives us p final v final to the power of gamma is equal to p initial times v initial to the power of gamma. I'll put a big box around this because this is what we wanted. This is a relationship between the pressure and the volume, and it's not a simple relationship because there's some crazy exponent that depends on the degrees of freedom, but this over here, this is the relationship that is used to actually draw the curve of an adiabat on the PV diagram. And this is how you would calculate the work done. You would rearrange this expression in terms of the pressure, right? Pressure is a function of volume, then you would integrate that with respect to volume, and that would give you the work done. So let's give a quick little summary as to what we did in this video. We started with the Equipartition Theorem and the First Law of Thermodynamics. We applied the adiabatic condition where Q is equal to 0 because there's no heat flowing in or out, and that gave us this equivalence between the change in internal energy and the work. Then we used this expression for the compression expansion work in a quasi-static process, and we used this negative sign convention. Then that gave us two different ways to write the change in the internal energy. We had this way over here from the Equipartition Theorem, and we had this way over here from this expression for work, for expansion compression work. That's what we had over here. Then what we did is we rewrote this pressure in terms of the ideal gas. We canceled some terms, we rearranged, we got this over here. And this links the differentials, the dt over t with the dv over v. This is a relationship between temperature and volume that is more natural out of these relationships that we have up here. But we didn't want that kind of relationship. We wanted a relationship between pressure and volume. So what we had to do is we had to integrate to take the cumulative effect of all of these tiny nudges along the adiabatic process. And then once we integrated, we evaluated the integrals and we got these natural logarithm expressions. Then we took the coefficients out the front of these natural logarithm expressions, and we ended up with this little guy over here, right? This is just the reciprocal of what we have downstairs. And this reciprocal, and this over here we have just exponentiated. Then we exponentiated both sides by going e to the power of this side, e to the power of that side. That got rid of the natural logs, and we just had this equivalence. We rearranged this equivalence to get this condition in terms of the temperature and the volume. Then we did a little manipulation using exponential laws, and we got this alternative relationship. After that, we took the ideal gas law again, we rearranged it for temperature, and we substituted that value in, and we canceled out these nKs, and we combined this volume, and we got an expression with the f in the exponent. And then we rewrote this exponent in terms of gamma. And gamma is this adiabatic exponent. And this is actually how you get to this final form, which is the most useful form of the condition between the pressure and the volume for an adiabatic process for an ideal gas. So this is the end result of this video. PV to the power of gamma, that is constant. Another way you can write it as is PV to the power of gamma, that is write that properly, constant. And that's what the Equipartition Theorem and the First Law of Thermodynamics state. This is constant. This product is always going to be constant.